Okay, please turn on your camera and mute yourself. And we're going to get started. So last week we talked about panel data, and it's still linear regression, but with the panel structure, you could either take the fixed effects or first difference, so that you take out the fixed components of the error and reduce the bias that comes from that fixed component. And today, so for this week and next few weeks, we're going to talk about models beyond the linear regressions that will be used for specific kinds of data. So today we're going to talk about some classification models. All right. So classification models are models where you're predicting not some continuous variable, but rather a category. So let's start from an example. So in this example, so this is actually the example that we're going to be working with for the in-class exercise on Thursday. So what this example is that in order to detect the potential discrimination against minority lenders for the mortgage lending, there is a US Home Mortgage Disclosure Act that requires the lenders to disclose the information of the applicants, and including their race and ethnicity. So then the data set we will be having is from the Federal Reserve Bank of Boston. And the data would include a bunch of applicants and their mortgage applications. And we see a lot of information about these applicants. There is a set of 38 variables in total, including their income and demographics like gender, age, including race, okay? And then it will tell you whether that person's mortgage application is approved or rejected. And now, suppose you are just an officer at the Boston Federal Reserve, and you're asked to test whether there is a discrimination. So how would you do it? So in this data, the outcome variable Y is whether this application is accepted or denied. So Y only takes two values. You can call it 0 and 1 because there are two categories. 0 if it's rejected, and 1 if it's accepted. Okay, so that's our outcome variable. It's not continuous. Any other value doesn't make sense. There's only two values. And the X variables are all the information that we have. So you have race, housing expense to income ratio, their debt payments to income ratio, which measures how indebted they are, their credit history, and their loan amount to the value ratio. So that's the LTV, meaning that you're borrowing 20%, oh, sorry, 80% or 70% of the housing value. Okay, so if you were doing a linear regression, you would do something like this, right? You have the Y variable, which is equals to 0 or 1, meaning that whether it's approved. And then you have the X variables on the right-hand side, and one of them is whether the applicant is a minority. And then you would do a t-test to see if you have a significant effect from that variable. And if it is significant, then it means that there is discrimination. So that's how you would do it in the linear regression. However, we talked about in the first class, whenever you have a dependent variable that equals to 0 or 1 and not continuous, when you do a linear regression, there could be some problems. So one problem is that your predicted value it may go out of the bound. So because x is continuous, and then the predicted value will also be continuous. So it will not be necessarily 0 or 1 or between 0 and 1. So it could be either negative or it goes up above 1. And in those cases, it doesn't really make sense, right? What does it mean if the predicted value is like -1? So we want something that predicts either 0 or 1 or something between, right? So if it predicts 0.5, at least it means that it has a 50% chance of getting accepted, right? But if it goes above 1 or below 0, then it doesn't really have any meaning. And then it also violates, of course, our blue assumptions. And that's because this would not be a linear function. So when you have a nonlinear function, then the errors will not have mean 0, and you will end up having biased and inconsistent estimates. So for all these reasons, linear regression is not the best model here, okay? And we have plenty of such examples in everyday life. So whenever in the medical experiments, you want to predict whether the patient will die or survive from some treatment, and there you have a 0, 1 variable, right? Whether either it dies or it lives. So it's 2 categories. And then if you want to predict the firm's bankruptcy, so that's again either it's bankrupt, which and then equals to 0, or it's not equals to 1. Or when you want to predict the default of like corporate bonds, whether it defaults or not. So only 2 values. So there are plenty of examples like that. And these are called classification problems because now we're not predicting some continuous variable. Like last week, we were predicting like the ROA, which is continuous variable, but rather the response variable is categorical, meaning that it takes either 2 categories or more categories. And then the goal is to classify each observation into one of the categories. Okay, so these are classification problem. And the most often way we use is called logit. So the idea of logit, it's actually quite simple. So basically, because you cannot have a linear function between x and y, so you just transform it into a nonlinear function. And then you write it in a specific form so that the prediction has to be between 0 and 1, okay? So what is the form? So this is the form that's that logit uses. So let's try to understand this thing. So we have the x here, okay? And there's a coefficient associated with the x. So it's just like our regression coefficient. And then add a constant beta 0, okay? So if you look at this part, beta 0 plus beta 1x, it's just like a linear regression, right? So it's a linear function of x. Now, we're doing a natural exponential function to that degree, okay? So E is the Euler constant, and we have e to the beta 0 plus beta 1x in the numerator, and then 1 plus that number in the denominator, okay? So what this does is it transforms the beta 0 to beta 1x, which is a linear function of x, to a nonlinear function of x. Okay, so this whole function here is nonlinear. And moreover, it will take a value between 0 and 1. So why is that? So this thing, of course, it can range from anything. It can go to negative infinity, it can go to positive infinity. So now let's suppose this beta 0 plus beta 1x is very, very small. So it's goes to negative infinity. And then e to the negative infinity would be what?
It would tend to 0.
10 to 0, exactly. So 0 divided by 1 plus 0 is equal to 0, right? So that this prediction would be 0 if it goes to negative infinity. And if it goes to positive infinity, it would go to infinity. So infinity divided by 1 plus infinity is equal to 1, right? Because that 1 plus is negligible compared to infinity. So we have, and this function is also monotonic in x, right? It's increasing in x. When x get bigger, this numerator would get bigger. And then the numerator divided by 1 plus the numerator would also get bigger. Okay, so this is increasing in x, and it ranges from 0 to 1. Okay. So it will actually never give you exactly 0 or exactly 1, but it's just a value between 0 or 1. And the interpretation, so that's our prediction, is the probability that y equals to 1. Okay. So for example, if it equals to 0.5, then what that means is that the probability of y equals to 1, whatever that category is, so in this case, the mortgage is accepted, the probability is 50%. So that's sort of the interpretation. And then we have transformed this linear function into a nonlinear function, which is increasing in x and takes values between 0 and 1. Okay, so that's pretty neat. And then you may wonder, why do we have this functional form? Because to transform something into between 0 and 1, there are many ways, right? Why do we choose this specific function right here with the natural exponential? So then you could actually derive this exact function using a very simple model. Okay, so this part is just to illustrate that it's not completely idiosyncratic function, but it actually has a meaning. But you don't have to necessarily know this. So in this simple model, consider you're a loan officer and you're deciding whether to either approve or reject. And then you get utilities from either approving the mortgage or rejecting the mortgage. Okay. And then the applicant has these characteristics x. And when you approve, you get a utility of theta a times x plus VA. VA is the error term. And then if you reject, you get theta r, so another constant times x plus another error. Okay, and then you decide to approve, of course, if the utility of approval is greater than the utility of rejecting. And then you would approve only if the difference between these two is positive. And what is the difference? You can just minus these two utility functions, and you get x times the difference between these two thetas plus the difference between these two errors. Okay, and let's call that part, call the difference p theta 0 and call the difference in the errors just the error v. And then the probability of y equals to 1 is equal to the probability that UA greater than UR, which is the probability that V is smaller than X times theta 0. And which then, if V is a random variable, and this is the CDF of that random variable at the point of theta 0x, okay? So now what is this probability? So we have to choose a particular distribution, and then we would just evaluate the CDF of that distribution at point x times theta 0. So the easiest, most natural distribution is, of course, normal distribution. So you could choose a normal distribution, and then you have the probability of y equals to 1 equals to the CDF of the normal distribution at beta times x. Okay. And again, this is actually the function. You will notice that, again, this is another nonlinear function, okay, of x. And it's increasing in x, right? Because when x is bigger, the CDF at beta x is bigger. And it takes value between 0 and 1, right? Because it's a CDF. So when this beta x is minus infinity, it goes to 0. And when beta x goes to positive infinity, it goes to 1. Okay. So again, we have a function that is increasing in x and takes values between 0 and 1. Okay, so this is actually another thing that you can use is called probit. So this is another nonlinear function to just transform the linear function into a probability. And then this is just describes what the CDF of normal is. So this is the PDF of normal. You just integrate to get the CDF. Okay, so logit is actually the CDF of a particular distribution, and that distribution is called the type 1 extreme value distribution. And that distribution has a CDF that equals to exactly this function. Okay, so this is a function that we see before for logit. And again, we have already discussed that this function is increasing in x, and it only takes values between 0 and 1. Okay. So then you can see logit and probit is actually similar. They're both just taking the CDF of some distribution at the value of beta x. Okay, beta x is just the linear function of x. It's like the linear regression. But then you do this transformation to evaluate the CDF of some distribution at that point, and that transforms it to a probability that that's equal to something between 0 and 1. All right. And then for logit, there is another thing that you could calculate is called odds. Okay, so the odds of something is just p over 1 minus p. So I don't know if you've been seeing the betting markets, right? When you say, for example, the odds of Trump winning the election is 3, it means the probability is equal to like 75%. So you have the probability over 1 minus 75%. So that equals to 3. Okay, so it's just another way to say probability. And here, when you have the probability that equals to this function, and then the log of the odds. So odds is this p over 1 minus p, and then you take the log of the whole thing. And that actually equals to a very simple function, which is just beta x, okay? So what this is saying is that for logit, if you take the log of the odds ratio, and that just goes all the way back to linear regression again. And this is kind of useful for talking about how do we interpret this beta, and we'll talk more about that later. Okay, so for now, what we've seen is that we have logit and probit. Both are, again, CDF functions of some distribution that convert the linear function of x into a nonlinear function that's increasing in the x and ranges between 0 and 1. And that's the trick, okay? And if you are curious what the logit and probit CDF looks like this. So you have the normal CDF. So you might have seen this before, looks like this. And then a logistic is just kind of similar, but it's a little bit more spread out. Okay. Now, now we want to know, how do we estimate this beta, right? Because this is our model. We have the probability of y equals to 0 is equal to some nonlinear function of x. And how do we estimate that thing? So the first natural thought is to just do the same thing as the linear regression, right? Remember, in linear regression, what we did is to choose the beta that minimize the MSE. The MSE is the mean squared error. Okay, basically, you calculate the square of the error of each observation, which measures how precise your estimation is, right? And then you take the average across all of the squared errors. And you want to minimize that because you want to get as precise a prediction as possible. But here, we can't exactly do that, right? Because what our outcome is only equals to 0 or 1. And this 0 or 1 doesn't necessarily need to have meaning, right? They're just two categories. And our prediction is a probability that y equals to 1. And you could take the difference between that prediction and the actual value of y. Okay, so that could be anything like 0.1, 0.5, 0.9. However, that does not necessarily have any meaning because we don't actually care about the difference, about the distance, right? We only care about whether you're predicting the right category or not. So here we were doing something different, which is called maximum likelihood estimation. So before, it's like a minimizing the loss function, where the loss function is the MSE. But here, it's a different kind of mindset where we maximize the likelihood of getting the data conditional on the parameters. So let's see what that is. Okay, so for both logit and probit, we have the probability of y equals to a nonlinear function of beta x. So we're just calling this nonlinear function g. So this is kind of generic. It can be any nonlinear function that is increasing in x and takes the value of between 0 and 1. So probit and logit are both special cases of the g. And then the way we estimate beta is we choose the beta to maximize the likelihood of observing the data that we actually observe. Okay. So we actually, in the data, we would observe a number of observations, right? For example, you have the x1, and then you have the y1, which equals to 1 or 0. And then you have x2 and y2 and x3 and y3, etc. And all the y's are either 1 or 0. Okay. So let's just take one of them, x1 and y1. Okay. So for that individual, it has xi, and then what is the probability of yi equals to 1? So that probability is just this nonlinear function, right? So that's the g of beta x is the probability that y equals to 1, given that you observe the individual has x. And then the probability that y equals to 0 is just 1 minus, right, that g function, g of beta x. Okay. And then you know that the probability that y equals to 1 is g of beta x, and the probability of y equals to 0 is 1 minus g of beta x. And then in reality, we will see that what the yi actually is, right? It's either 1 or 0. So if it's 1, the probability that we observe the actual data is this. If it's 0, and then the probability is this. Okay. And so why do we want to do that? So let's say we make this calculation using some beta. And then it gives us this is equal to 99%. Okay. And this equals to 1%. And then in reality, if we see that y equals to 0, for example, and then we know that probability is only 1%, which is pretty unlikely. And then we would think, oh, there might be something wrong with that beta. So because if indeed that beta is true, then the probability of us actually seeing y equals to 0 would be highly unlikely. So that maybe beta is just equal to something else. Okay, so maybe for another beta, you have this probability equals to 20%. This probability equals to 80%. And then we would say that the other beta is better, right? Because it gives a high probability of we actually seeing the y equals to 0. So that's kind of the idea that we are taking the data that we actually see, which is the reality. And then we take a bunch of values of beta and calculate what is the probability of us seeing that reality. And we want to maximize that probability, right? Because what we see is the reality, is the data that's generated from the actual beta. And we don't want some beta that makes the reality we observe very unlikely. Okay. So that's only for one observation, right? And you have many observations in the data. So then you just calculate what is the probability for you to see all of your observations. And assuming that all of your observations are independently drawn from that distribution. And then what you do is just to multiply all of the probabilities, okay? So this is kind of like if you have a jar with 20 red balls and 80 black balls, and then you're drawing from that jar with replacement, and then the probability of drawing 3 red balls would be 0.2 to the third degree, right? Because that's just 0.2 times 0.2 times 0.2, because you're drawing 3 times, and those are independent. So you just multiply these 3 probabilities. Same thing here. So if you have n observations in the data, and then you just look at the first observation, and given the x of the first observation, what is the probability of us observing y1? And that y1, you just take the actual value, either it's 0 or 1, and then do the same thing for the second observation, and so on and so on. So you do it n times and then multiply them all together. So that's the likelihood of you observing all of the data you have. Okay, and that is a function of beta. So this is a function of beta. It's also a function of x, but we know x, right? So we can just insert the values of x and y into this function and calculate this function for any value of beta. And then we want the beta that maximizes this function. So that maximizes the likelihood of us seeing the data.
But first of all, we need to know whether the y is 0 or 1, right? That's our prerequisite according to your logic.
Yes, we know that, right? Because that's in the data.
Oh, right, sorry. Yeah.
So take any data, you will know that whether the first observation is 0 or 1.
Right.
And if it's equal to 0, then this is f y equals to 0 conditional on x1, which equals to 1 minus g of beta x1, right? And
right. Yeah, we know that.
Right. And if it equals to 1, then this just equals to g of beta x1. Okay, so depending on what is the data that we observe, this can take either g of beta x1 or 1 minus g of beta x1. So that's why we are writing this function f here, and f equals to g of beta x1, beta xi, if y equals to 1, and equals to 1 minus g if y equals to 1 minus y equals to 0, sorry. But these are just notations, okay? So the thing we're doing here is what I've already described. For every observation, you have the x, you have the y. So for any beta, you can calculate the probability of you seeing that y given x. And then you do it for all the observations and multiply all the probability together. And that is the likelihood you get here. Does that make sense? Okay, and this is it. So this is the maximum likelihood estimator. And then you find the beta that maximizes its function, and that's the beta you choose. Okay, that's our estimated beta. And so this is multiply a bunch of things together. And usually in calculation, we would just take the log so that you don't have everything multiplying each other, but rather just a sum of all the log of g prime x beta. but again, this is just a notation. And what's important here is to understand the logic of the maximum likelihood, which is to maximize the likelihood of we observing the data. Okay. And this is different, as I said, a different mindset as the minimum squared error, which, so the mindset there is to try to minimize the error between our prediction and the actual value. Okay. But here, it's another way of estimating, which is to maximizing the likelihood of observing our data given the parameter. And so these are two different ways, but actually they are equivalent in many cases. So for example, for OLS, when you're doing the linear regression, you can also calculate the likelihood. Okay. So you have the Y, you have beta X, and then you have an epsilon, right? And you can assume that epsilon is normally distributed. And then for each X and Y, you can also calculate kind of the probability. So there is not a probability, but rather a density. So it's a density of you observing that Y. And then you can calculate that given the normal distribution. And when you do that, it will actually give you the same answer. It will give you the same beta as you would get using the ordinary least squares. But here for logit, we actually can't do that. We actually cannot just minimize the errors. So the log likelihood, maximum likelihood would be the way to go here. Okay. And a few more words about the maximum likelihood. So it's actually a very powerful estimator. And for OLS, we say that it is blue under some assumptions. Okay. So here it is actually the BUE, so BUE, which means that it's the best unbiased estimator because it's not linear. Okay, so if you have a sample size goes to infinity, and under some assumptions, it is actually the best unbiased estimator, which is pretty good. And as I just mentioned, so the OLS is actually also, you can get it same way using the maximum likelihood if you assume that the errors are normally distributed. But we don't use that as much, right, except for logit here. And the main reason is that it requires that we have to specify the distribution. Okay, so for logit, we are assuming that there is a distribution, the type 1 extreme value distribution, which gives the specific functional form that we just saw. And then you can also do probit, but also you have to assume that the distribution of that thing is normal. But whatever you do, you have to assume some distribution. Otherwise, you cannot calculate the probability, right? So that's kind of the drawback. And whatever distribution you do, even though normal distribution is the easiest distribution already, it's still usually very complicated to do the maximum likelihood and to estimate that. And especially in the old days when the computer are not as great. So now actually it's used more often, like the maximum likelihood and also GMM, which is a more complicated version of this. And actually, we're also going to see this again in 2 weeks when we talk about the survival analysis. And there, it's also estimated using the maximum likelihood. So it's still very useful in many settings. And then, so we talk about what logit is. So it's a nonlinear function, which you can think of it as the CDF. And we talk about how to estimate it. And now let's say we estimate it. successfully, and we find this beta that maximizes the likelihood. Okay, so that's the beta we want. And then the next question is, how do we conclude from that beta, right? So let's say the beta equals to something, and then what does that even mean? And that's also not obvious. So in the linear regression, the meaning of the beta is pretty obvious. Okay, so it's literally when x increases by 1 unit, y increases by beta. It's as simple as that. But here, you don't have that because it's a pretty complicated nonlinear function of x, and you have to calculate, given the beta and given x, and calculate what's the change of y in response to change of x. So let's say we still want that. We still want to know what is the marginal effect of x on y. So let's say for policy or whatever reason, we want to know if we increase x by 1 unit, what is the effect of that on y, okay? And now you would actually just take a derivative of your prediction, which is the probability of y equals to 1, and take a derivative with respect to x. And this part, right, we wrote it as the big G of beta x. And we take the derivative, we call that derivative the small g. It's also beta x, but also multiplied by beta, right? Because we're taking derivative with respect to x, and this thing inside, when you take derivative with respect to x, it equals to beta. So this is not as simple as linear regression, because linear regression, this whole thing would just equals to beta. But here it's beta times this thing, which is the PDF of G. Okay, which is also the derivative of G.
That's the chain rule, right?
Yeah, it's the chain rule, exactly. Because you have G is a function of beta x, but then beta x is a function of x. So when you take derivative with respect to x, you need to take G with respect to beta x, and then multiply by beta x, taking derivative with respect to x.
Thank you.
So that gives you here. All right. And this is the marginal effect of x. Okay, so if you want to know the answer to the previous question, you need to calculate, first of all, beta, and then at particular x, what is the PDF at beta x, and multiply those two numbers, and that gives you the change in y in response to 1 unit of change in x. And one observation here is that G is always positive, right? Because the big G is an increasing function of x. So when that takes a derivative with respect to beta x, that's always positive. And when you multiply a positive number by beta 0, and then this whole thing will just have the same sign as the coefficients in beta 0, okay? So you can still say, whenever you see a positive beta 0, you can say that when x increases, the probability of y equals to 1 would increase. The other way around, when beta is negative, you can say that when x increases, the probability of y equals to 1 decreases. Okay, so the sign is still the same, but the magnitude, you have to do this extra step here. And then another thing I'll observe here is that it's not only a function of beta, but also a function of x, which means that the marginal effect is different for different x's. And this makes it a little bit complicated. Like for policy, you may want to know on average, when I increase x, how does y change, right? I don't want to know it for only one single x, but I want to know for many, many x's, what is the average? So then you can do something called the average marginal effects, which is just to take the average of that previous marginal effects here, but taking the average across X, okay? So it's the expectation of this small g beta X and taking that expectation across all the X's and multiply it by beta. Okay. And if you have n observations, you can just calculate the expectation as the average of the small g at each X, and then multiply that by your estimates of the beta. So this is just letting you know to understand how this works, but actually in Python, I'll do it automatically for you. But when you see that beta, don't think of it as the marginal effect of X on Y, but you need to know that you need to take this extra step to actually calculate the marginal effect. And then going back to the odds, okay, remember we have the log of the odds ratio. And for logit, it just equals to beta X, okay? And another way to say this is that the odds, which is P over 1 minus P, is equal to e to the beta X. And now for a 1 unit increase in X, these odds would just become e to the beta X plus beta, right? Okay. And what does that mean? It means that a 1 unit increase in X is associated with increase in the odds of this much percent. Okay, so let's just try to digest this using an example. So let's say beta equals to 0.05, okay? And then this odds is equal to e to the 0.05x. And then when you increase x by a unit of 1, it becomes e to the 0.05x plus 0.05, which equals to e to the 0.05x times 1 plus e to the 0.05. And then this thing would just be approximately 1.05, okay? Because e to the 0.05 is approximately 0.05. And this then this is just the value before times 1.05, okay? So which means when beta equals to 0.05 and when x increases by 1 unit, and that predicted probability, sorry, this is the odds. So the odds goes up to by 5%. Okay, let me say again. When beta equals to 0.05 and when x increases by 1 unit, the odds ratio increases by 5%. So that's the interpretation. Okay, so that 5% is 100 times beta 0. 100 times 0.05 equals to 5. So that's another way to interpret this. Okay, so you now have 2 ways, but this is only for logit. Doesn't work for the other distributions. So for logit, there are 2 ways to interpret. You can either do this marginal effect calculation and say when x increases by 1 unit, how does that change the probability of y? And you calculate this. Or you can say that when x increases by 1 unit, the odds ratio increases by 100 times beta 0%. Okay. And odds ratio just corresponds 1-to-1 to the probability. So that's also a meaningful interpretation. Okay, one last thing. Okay, so now we've talked about how to estimate a logit, and once we get the estimates, how to interpret those. And then the last thing we want to know is how good is our prediction? Okay. So why do we want to know that? Just like in the OLS. So in an OLS, what is the way you would do to know how good is that prediction? So you can always have a very good prediction, right? All the x's is very predictive of the y, or you can have y is totally unrelated to x, and then even if you do a very good linear regression, it's still x doesn't predict y. So how do we assess whether how well x predicts y in linear regression?
R
Software?
R squared, very good. So R squared, basically what that measures is how big the residual is, right? And when the residuals are small, it means that the predicted value is pretty close to the true value, and then we have a good prediction. But when R squared is very low, it means the residuals are big. So again, you can apply that exactly the same logic here, because the residual doesn't have much meaning here, right? What we predict would be a probability. And taking the difference between that probability and 0 or 1 doesn't really make too much sense. So what we have here is something called the ROC curve. So this is actually a little bit hard to understand. So let me try to explain that just step by step. So what this curve does is it plots two things against each other. So the first thing is called the true positive rate. Okay. So basically, when you do a prediction, okay. So let's say this is the truth, okay? And this is your prediction. Let me just try to draw more nicely here. Okay, so let's say the rows are your prediction, the columns, and the rows are the truth. Okay, so if the prediction can take the value of 0 or 1, and truth, let's say, also takes value of 0 or 1. So right now it's still right now it's a little bit different from logit. Okay, but just bear with me for a second, because in logit our prediction is actually not 0 or 1, but it's like continuous probability. But let's say the prediction is 0 or 1, and the truth is also 0 or 1. And then we could have four cases, right? Either prediction is 0 and truth is 0, and that's what we call true negative. Right? Because it's negative and we predicted correctly. And when the prediction is 1, and when the truth is 0, So it's still negative, but we predicted a positive. We call that a false. So we call that false positive. Okay, because we find a positive, but it's actually false. And then when the truth is 1 and prediction is 0, we have a false negative. And then we have a true positive if it's both 1. And then the true positive rate is equal to the true positive. So this thing here divided by itself plus the false negative. False negative is here. Okay, so what that means is when the truth is 1, when the truth is positive, what is the probability that you actually find a positive? And then you have the false positive rate, which is the false positive here divided by false positive plus the true negative here. Okay, so and that means when the truth is 0, when the truth is negative, what is the probability that you find a positive? And a useful prediction will always have the false positive rate. The true positive rate is greater than the false positive rate, right? Because this true positive rate is the probability you predict a positive when it's actually positive. And then the false positive rate is the probability you predict a positive when it's actually negative. So a useful prediction, you should always predict positive more often when it's actually positive, right? So a useful prediction will always have this rate higher than this rate. And when we plot these two numbers, a completely useless prediction would just be the diagonal. So you have these two rate equals to each other. Okay, so that's a completely random prediction. Whatever the truth is, you always predict positive with some probability. Okay, and whenever you get the y-axis, the true positive rate greater than the false positive rate, and that improves the prediction. So this is a better prediction than the diagonal, and then this blue line here is an even better prediction. Okay, now let's map this to Logit. So for Logit, you have a bunch of predicted probability, right? So you could, so that probability goes from all the way from 0 to 1. And then you can set a threshold. Any threshold. So below that threshold, you say it's a negative, that the predicted value is 0. And then above that threshold, you say it's a positive. And then you move this threshold from 0 to 1. Okay. So when the threshold is at 0, what happens? Well, when the threshold is at 0, nobody is negative. You always predict positive, right? So when you always predict positive, both the true positive rate and false positive rate is equal to 1. So you have this guy here. And then when this threshold is at 1, for example, it means that you predict 0 positive and everyone negative, okay? And then both the true positive rate and false positive rate is 0. So you're at this point. And now let's look at some threshold in the middle. And then you have, you're predicting some positive and some negative, okay? And among all the true positives, you will predict some of them to be positive, and among all the true negatives, you would predict some of them to also be positive. So then you have some value that's along the line somewhere. Okay, so then when you move the threshold all the way from 0 to 1, and at any threshold, you could have a point, and then you connect all of the dots, and you would get the ROC curve. Okay, so let me say again. So logit is when you predict a probability that is continuous from 0 to 1. And when I set a threshold, and below that threshold, I call it negative. Above, I call it that positive. And when I move that threshold for the threshold at any given point, I can calculate what is the true positive rate and the false positive rate. And then I can find a point in this diagram. And then when I move that threshold a little bit more, and then I find another point, and I connect all the points, and it will become a line that goes from 0, 0 to 1, 1. Okay. And if it's a useful prediction, it will be above the diagonal. And the more above the diagonal, the better, because a perfect classifier, what would be a perfect one? The perfect one is just a dot here, okay? Which means that the true positive rate is 1. When it's positive, I always predict it to be positive. And the false positive rate is 0, meaning that when it's actually negative, I never predict to be positive. Okay. So the best case would be here, and you can always go closer and closer to it. So when you are closer to that point, the better. So then we have a statistic just calculating kind of the area between the curve and the diagonal. Okay, so you can see that. So this is the diagonal. So for a perfect prediction, you have that area equals to half of this square, right? And for a slightly worse prediction, you have the area equals to this. And for even worse prediction, if it's very close to the diagonal, then this area would be very close to 0. Okay. So that is called the area under curve, AUC. And that would be a statistic to evaluate how good that prediction is. It's kind of like the R squared. Okay. The bigger, the better. If it's big, if it's very big, it means that I always predict positive or negative correctly. If it's small, it means that I'm close to a random prediction. Okay, I'm just flipping the coin and randomly saying it's positive or negative, but without looking at any of the x's. So you can also calculate both of these. You can also both plot this ROC curve and calculate that area under curve using Python, and that will actually be an exercise in your first problem set. Okay, so that's how you evaluate the prediction here. You can think of it as the R squared for classification models. Okay.
I have a question. So what is the maximum value for ROC, like the first case? Is that 100% or 50%?
I don't know if there's any normalization. Yeah, it's either 0.5 or 1, I guess.
Okay, so what should be considered as a good threshold? Like 80% or
Depends.
90% above?
It depends. Like
Oh.
there's no absolute standard for R squared. So sometimes a 0.1 R squared is good. Sometimes it's bad. Depends on the scenario. But I would say whenever the AUC is positive, it means that the prediction is still useful.
Okay.
And when and I guess there is a maximum value, either it's 0.5 or 1, I don't actually remember, but the closer you get to that maximum value, the better. Yeah,
Okay,
there's
thanks.
no absolute criteria to say it's good or bad, but it gives you how good it is. And then this can allow you to select the right variables, right? So if you have two x's and you want to see which one is stronger, and you can always compare them, which one gives me the better prediction.
Okay, thanks.
Kind of like you do the stepwise selection in the linear regression, right? You select the x's that more strongly predict your y. So you can always compare different models, and that gives you which one is better in terms of the prediction. Another question from Shirley.
Yeah, I just want to follow up on that. Is there the best threshold? So in this case,
Is there a bad threshold? Sorry, what is it?
the best threshold point.
Oh no, it's you always move the threshold all the way from 0 to 1. If it's at 0, as I said, it will give you this point, because for all the RC curve, it always passes through these 2 points. One is the 0, 0 point, and the other is the 1, 1 point. Okay, and that corresponds to when you are putting the threshold at either 0 or 1. So you're saying all of the prediction is positive or all of the prediction is negative. And then for everything in the middle, you have something along the curve.
I see.
So that threshold is always moving, and when it moves all the way from 0 to 1, it maps out the whole curve for you.
Oh, so the curve is made up by the threshold points.
Yeah, each point on the curve corresponds to just one threshold.
I see.
Yeah.
So do we necessarily need to find like a best threshold point along the curve?
There's no best threshold. So the threshold always moves. So
Oh.
you're not evaluating the threshold, you're evaluating the model. You're
Right.
evaluating whether my x's predict the y. So the threshold always moves. That gives you the curve, right? The curve is your prediction. It's not any given point.
Yeah, got it. Thank you.
Okay. All right. Any other questions before I move on to other classification models? Okay, so that's Logit and Probit. And then we'll cover a few more others. So these others are useful for cases where you have often more than 2 categories. Because for Logit and Probit, you only have y equals to 0 or 1. So there are only 2 categories, but sometimes you have more, right? So for example, let's just say that your outcome is which bank you borrow from, and that can be either Bank of America, JP Morgan, Wells Fargo, one of many banks, right? So it can take many categories, but still it's not a continuous number. It's just a bunch of categories. And for example, location of the firm where it decides to locate, it can be in New York State, California, DC, etc. And for firm, you choosing which target firm to acquire, that would be another category. Or when you're choosing which Master of Finance program to attend, you have these several schools, and then each school is a category. Okay. And in this case, it's basically a slight generalization of logit. Okay, so that's what we call the multinomial logit. So here we have a function which is also nonlinear in x, which also looks like the logit function. So you have the natural exponential of beta x in the numerator. And then here you have the beta for each specific category. Okay, so you have beta j for the j category, for example. And then divided by the denominator is the sum of the natural exponential of all the beta x. Okay, and each beta corresponds to a category. And that is the probability that y takes that jth category given x. And again, this will be an increasing function in x, and it will also be taking values only between 0 and 1. Because when this beta x goes to negative infinity, this probability goes to 0. When it goes to positive infinity, this probability goes to 1. So it's exactly the same as before. And also, when you have 3 or more categories, you can always normalize one of them to be the baseline category. So normalize one of the betas to be 0, which is actually what we did in Logit. In Logit, we are normalizing the y equals to 0 category to 0. And then we only have one beta, which is beta corresponding to the other group. But when you have 3 groups, then you would have 2 betas. Okay.
Does the denominator sum to 1 in that probability function?
All the probabilities sum up to 1. Okay, so let's just do a simple example here. Let's say if there are 3 categories, and then the probability of yi equals to 0 equals to, let's say we normalize that to be 0, and this will equal to 1 over 1 plus e to the beta 1x plus e to the beta 2x, okay? And the probability of yi equals to 1 equal to 1 over, not 1, e to the beta 1x over 1 plus e to the beta 1x plus e to the beta 2x. And then probability of yi equals to 2 equals to e to the beta 2x divided by same thing, okay? And then you can see that these 3 numbers sum up to 1. So you're always predicting these 3 probabilities, which is the probability in each category.
Professor,
Yes.
you're saying that this case is like when we have 3 categories, right?
Yeah, if you have more, you just do more like this.
Okay, thank you.
And you have to, if you have 2, you're just back to Logit, right? Because in Logit we have probability of y equals to 0 is 1 over 1 plus e to the beta x, and then the other one is e to the beta x over 1 plus e to the beta x. So Logit is just a special case of this. And then same thing, we do maximum likelihood, so we can calculate for every observation. Let's say, again, we have 3 categories. And then for each observation, if it takes value of 0, and then we use this function, takes value of 1, we use this function, takes value of 2, we use this function. Okay, so we can calculate the probability of observing each point in our data, and then we multiply all of the probabilities. That's the likelihood of observing the whole data, and we maximize that probability now with respect to beta 1 and beta 2. So that's how you would estimate that. And you could also calculate the marginal effect, which is, again, just taking the partial derivative. Okay, so that's multinomial logit, which is just an extension of the standard logit model. And next, let's talk about ordered probit and ordered logit. So here, we also have more than one category, more than 2 categories, okay? However, the difference between these and the previous case is that these categories are ordered, meaning that there is a natural order among them. One is better or higher than the other, and then can order them from the highest to the lowest. So this doesn't matter whether it's ordered or not when you only have 2 categories, right? Because when you have 2 categories, it's always kind of ordered. But when you have 3 or more, it's different. It's a different case whether it's ordered or not. And examples of this can be the number of cars, 0, 1, 2. These are different categories, but there's an order among them. And a very good example is the corporate bond ratings. So you have the AAA, AA, A, and BBB, etc. Okay. So this is a perfect example to use the ordered probit because you have these categories, and AAA is better than AA, and again that's better than single A, and then that's better than BBB. So it's ordered, and it's not continuous, which means that one thing you could potentially do is just to convert these ratings to numbers, right? I can call AAA to be 5 and AA to be 4, A to be 3, and that 2, etc. And then I can have a continuous variable again and do linear regression, but it doesn't work that way because the difference, right, between AAA and A and AA may be very different from the difference between AA and single A, right? And when you fall from A to B category, and maybe there's a drop in that, and there's like the investment grade and there's the speculative grade. So there are some discontinuous jumps there. So it's definitely not continuous. The difference between any 2 categories is not the same. Okay. And then another example, you could have different categories for what are the controls on foreign direct investment. 0 is no restriction, 1 is moderate restriction, 2 is severe restriction, something like that. Or you can have different categories for your political view, whether you're a strong Republican, weak Republican, kind of neutral, or weak Democrat and strong Democrat. So again, those are ordered along a scale, right? But it's not continuous. So when we have something like this, we could do multinomial logit, but that doesn't account for this information that they're ordered, right? So it won't be very efficient. And the better way to do here is just to use what we call an ordered probit logit. So what that does is that, remember before, for logit and probit, we have this G of beta x, right? That's the probability of y equals to 1. And G can be a CDF of some distribution. So it's just, this is just the probability of that random variable under, is below beta x. So it's kind of like drawing this normal or whatever distribution, and then take beta x, you calculate what's the probability under that value. And here, instead of doing just one single cutoff, we're doing multiple cutoffs. Okay, so again, taking any distribution. Let's say we have two cutoffs, and if this random variable is above the higher cutoff, then the bound has a AAA rating. And then when it's between these two cutoffs, it has an A rating, a AA rating. And then when it's below the lower cutoff, it has a single A rating. Okay, and this is just a generalization of the previous case. Okay, and then you could calculate this. Let's say this cutoff is called C1. This cutoff is called C2. And then once we have the CDF of this distribution, we can calculate what is the probability of that random variable being below C2, what is the probability of it between C1 and C2, and what is the probability of being above C2. And that all be functions of the CDF. So
Sorry, I have a question. Sorry to interrupt. So those cutoffs are arbitrary, right?
Yes, but it will be something that you estimate. So these cutoffs are just like betas. So you need to estimate them. You have a very good point that the choice of the cutoffs are very important, and it depends on what your data is look like. You can choose different kinds of cutoffs to get closer to the data, right? So for example, if the data has very few AA observations, then you would want to choose these cutoffs to be very close to each other, right? So there are not many observations between them. Or if there's very few AAA, let's say that's very hard to get, and then you would want to choose this C2 cutoff to be very high.
Right, right.
So that does not happen very often. So these cutoffs are entirely chosen by us. So we will need to estimate them. Okay. So given these cutoffs, you can calculate the probability. So you can take a look here about all the probabilities is just a function of your cutoffs and also the beta. Okay. And then your likelihood would be something like this. Okay, so I won't go into the details, but I just want you to understand the intuition. So you have these, let's say you have these three categories, and then you take all the observations that in the first category, and for each of them you calculate what is the probability, and multiply them all together, and then do the same for second category. You actually do that for the same observation as we did for logit, and then this product is the likelihood, and then you can see that this is a function of both the beta and the cutoffs. Okay, so you have a bunch of C1 and C2 in there, and you also have the beta. So then you want to maximize that likelihood with respect to both beta and C1 and C2. Okay, So this would also be something you estimate. And your estimates would give you the beta and the cutoffs. And then with those parameters, you can calculate, you can give prediction for any X.
So I missed it. I think what is the relationship between what is the relationship between the cutoff and the beta here? I don't get it.
There's no relationship. They're just different
Right.
parameters.
Yeah, that's what I'm thinking about. Thank you.
Yeah. So yeah, actually you can think of Logit and Probit just like special cases of this where we have a cutoff of 0 or something like that. So it's just one fixed cutoff. But here we have several categories, so we need to have several cutoffs, and we will also choose those cutoffs to maximize the likelihood. Okay, so that's the intuition. Okay, it looks very complicated in math, but the intuition is just what I have described. And all of your predicted probabilities by construction, they will also add up to 1. Okay, because it's the probability that you either below that cutoff or above that cutoff or between those two cutoffs. And there is the ordered Logit and there's the ordered Probit. Again, it just applies to different distributions. Depends on what you choose for this distribution. If it's a normal, then we call it ordered Probit. If it's the extreme value distribution, we call it the Logit. But in practice, as you will see in the exercise on Thursday, the particular distribution usually doesn't matter. Okay, so you will often see that Logit will give very different conclusions from the OLS regression. However, Logit and Probit usually gives similar conclusions. So the actual distribution usually doesn't matter that much. So you can just choose one of them. Okay, so and then on Thursday, we will go through this example and we'll also talk about one more thing, which is how to do the inference, because in the linear regression, we have that assuming that the errors are normal, and then we have a very nice formula for what is the standard error of the estimator, and also the distribution is the t-distribution, right? So there you can just do the t-test. However, here it's a very complicated maximum likelihood estimator, and there's no, we don't know what the distribution is. And if you want to know the distribution of that estimator, if you want to know its standard error and do hypothesis testing, for example, what we usually do is just to bootstrap. So we'll talk about that, also about that on Thursday. Okay, so before I let you go, let's just do 2 quick poll questions. Okay, the first question is about how do you interpret the coefficient from the Logit. Let's say you have a Logit model, your Y variable is whether the firm defaults on its bond. And then the X variable is revenue growth rate, and estimate coefficient is of beta is minus 0.1. And I want to know if there's a 10% increase in that X variable, how does Y change? Or how does the odds change? Okay, 20 more seconds. All right. Okay, so about half of you chose increases the odds by 1%, which is the correct answer. So as we discussed, for logit, the beta is not the marginal effect of x on y, which is unlike the linear regression. For the marginal effect, you have to multiply beta by the small g of beta x, right? Because that's the derivative of that probability with respect to x. And here we don't know what that small g is, because I'm not telling you what is the distribution and what is the value of the x. So you don't know what the marginal effect exactly is. You know that it's negative because the sign is negative. However, for odds ratio, there is a clear interpretation that when x increases by 1 unit, y changes by 100 times beta. Not y, sorry, the odds ratio changes by 100 times beta percent. And here, when x changes by 0.1, the odds ratio would change by 10 times beta. 10 times beta here is 1, so that changes by 1%. Okay. Any questions about this one? Okay, so just one more. So here I want to know if you want to predict how a startup exits, whether it's being acquired or goes to IPO or just remain as a private firm. So there are 3 categories here. Okay, there can be more, but let's say there are just these 3. And what model should we use? Okay, 20 more seconds. Okay. So logit, probit, they're only for when you have 2 categories. So it's 0 or 1. So here you have 3. So you would need to use multinomial logit. It's also not ordered probit because these are not actually ranked. So there's no option that's necessarily better than the other 2. So it's not, they cannot rank from best to worst or highest to lowest. And when it can be ranked, we will use ordered probit, like corporate bond ratings. Okay, so on Thursday, we'll go through this example of the mortgage application that we talked about at the beginning. So I will upload some of the codes to Google Drive so you can take a look if you want, but you don't have to. And then two other things is, first is for the problem set. So I made one very small change. I actually deleted one of the small parts of the third question. I also posted an announcement on Canvas. So if you downloaded the problem set from last week, then you might want to re-download it. But actually doesn't matter because I only deleted one of the parts, doesn't add anything. And the other thing is you should fill out the survey sent out by the TA, asking about which time zone you are in, because we're going to allocate you into groups by the end of this week. So then you can start working on the final project, which is 3-4 weeks away. And one of you suggested to me that I should put the people in the same time zone together so that you don't have to coordinate across different time zones. And I think that's a good idea. So you should fill out that Google spreadsheet so that can help us allocate. Okay. So that's all for today. And I will have office hours until 10. And you're welcome to stay if you have any questions.